Okay, let's start off with we'll get going on section 2013, preparation and reaction of nitriles. So stop the video, share the screen, and get the PowerPoint slides going. Okay, so preparation of nitriles. We've seen this multiple times already where we can just do a simple SN2 reaction with sodium cyanide. So of course it works well for primary or secondary, methyl of course being the best. We can convert our alkyl bromide into a nitrile. And remember, nitriles are part of this class of carboxylic acid derivatives. At first glance, it doesn't look like they should be, but the carbon is attached to nitrogen with 3 bonds. So it has 3 bonds to a more electronegative element. And so if I look at a carboxylic acid is the carbon of the carbonyl there has 3 bonds to oxygen. So the first one we'll look at outside of this straightforward SN2 is a dehydration reaction using thionyl chloride. In the previous slides for the section on amides, I showed that we could do this with some phosphorus-based reagents, and that is possible too. But we'll do this with the thionyl chloride to match what's in the textbook. And so this mechanism is a dehydration of an amide. First step is the amide acts as a nucleophile on our thionyl chloride. And just like when we've used thionyl chloride before, we're setting up a situation where we have a really nice leaving group. So in this case, we lose a chloride here. And so this is very similar to the mechanisms we've seen for thionyl chloride and other reactions like making alkali chloride or making an acid chloride. In this reaction, it's a little bit differently. We have a base here to remove this proton. And then we're left with this intermediate. And the last step here, instead of kind of a nucleophilic attack followed by loss of a leaving group, we're using it as a leaving group to help an elimination reaction. And so we get a proton transfer. So that base can remove this proton so we can form this carbon-carbon triple bond. But in this case, this is acting as our good leaving group to help to affect that elimination. And so we get the leaving group leaving like this. And so ultimately we have our nitrile. If you follow the curved arrows here, we've produced sulfur dioxide, sorry about that little glitch, and chloride. Okay, so 2 ways to make the make the nitrile. Let's look at some reactions in the nitriles. And again, we saw a couple of these reactions in the aldehydes and ketones chapter when we looked at making this, making the cyanohydrins. So the first one we look at is the acid catalyzed hydrolysis of the nitrile. And then we'll look at the base catalyzed hydrolysis of the nitriles. Both of these will give us an amide as the kind of initial product. So that's what's shown here. And then the rest of the mechanism is in this case, will be the acid catalyzed hydrolysis of the amide that we've talked about previously. But let's look at the acid catalyzed hydrolysis of the nitrile. Again, I don't think you will be too surprised at what the first step is. We have our hydronium ion. We're going to have a proton transfer. This, of course, helps make the carbon here more electrophilic, so water can attack. So I'm not going to say nucleophilic attack at the electrophilic carbonyl carbon, but I am going to say nucleophilic attack at the electrophilic nitrile carbon. But it's the same principle at play. Now we have this kind of intermediate. And we're just working on that kind of first part of the reaction scheme we had on the previous slide. So we're working on getting towards having an amide. Now we've got some proton transfers to do. Sorry, let me just correct that. I've lost it. Apologies. And we'll get there. Okay, so we've got some proton transfers to do. So water will act as the base, remove this proton, and then the hydronium ion will act as the proton source. So we have our second proton transfer. And if I draw a resonance structure of this, let's see, we'll end up with a species that looks like this, which is what you get if you have an amide and you protonate it. So the textbook shows the deprotonation, but if you were going to continue this on, and you should be able to do this, you could practice, continue this on to finish up the hydrolysis. Come back. You would be able to get from here to here using the hydrolysis of the amide mechanism. Okay, so let's take a look at the base catalyzed hydrolysis of nitrile. And again, as you might expect, this one is going to be more simple in that you have less steps because we don't have as many proton transfer steps going on. We do have some, but we don't have anywhere near as many. So let's take a look at a place to put these. I'm going to do it on this slide. So our first step is our nucleophilic attack with the hydroxide as the nucleophile. To generate this intermediate, I'm going to redraw my hydroxy group because we need to do a proton transfer here. But before we do the one down there, we're going to put a proton transfer here. And again, basic conditions, we are not seeing any positively charged intermediates. And now, of course, I forgot that I wanted to have it drawn so I could do that proton transfer. So let's go and get that there again. So we take the hydroxide, we'll do a proton transfer here. Now we're going to have an intermediate. It's got a negative charge on the oxygen. We really need to get to the stage where we have the amide, so I'm going to draw a resonance structure. Now this resonance structure has a negative charge on the nitrogen, and it can get a proton from water, which of course is our proton source under basic aqueous conditions, and we are left with the amide, and then the rest of the mechanism is the same as the basic hydrolysis of the amide to give us, oops, the carboxylic acid after the aqueous workup. Okay, let's take a look then at some reactions of the nitriles. I'm going to look at the reaction of nitrile with reduction. And this will give us an amine where we've added 2 hydrogens to this carbon and 2 hydrogens to that nitrogen. And so it's related to, the reaction we saw at the start of this chapter back before the spring break and the craziness that happened. We'll see that the reaction here gives us an amine. In the reaction of the excess lithium aluminum hydride with a carboxylic acid, we produce an alcohol. So the other reaction we're going to look at for nitriles is the reaction with Grignard. And here there's a little bit of difference. Most of the other ones we looked at, so the reaction of the ester with a Grignard, the reaction of an anhydride with a Grignard, and the reaction of a acid chloride with a Grignard. The Grignard adds twice to give you a primary alcohol. Sorry, a tertiary alcohol. Here we end up with a ketone. So let's take a look at why we only get the addition of one equivalent of the Grignard. So we'll look at the mechanism. So the Grignard, remember, is a nucleophilic species. We get nucleophilic attack at the electrophilic nitrile carbon. And our intermediate looks like this. Let me just make that R group different. And when we take a look at that intermediate, we've got a carbon-nitrogen double bond. So why can't a second equivalent of the Grignard add to that? What would the resultant species look like? If we were going to do a second step that looked similar to this first step, that nucleophile would have to come in, and the pair of electrons from the carbon-nitrogen pi bond would end up going on the nitrogen, and we'd have to generate a -2 charge on the nitrogen. So that's really unlikely to happen. So it stops after this first addition. Under those aqueous acidic conditions of the workup, you produce an imine, and hopefully you remember that an imine under aqueous acidic conditions will be hydrolyzed to give you a ketone. Okay. So that actually finishes our section on nitriles. Let me come back a slide here and talk about some good questions from this section. Really, any of those conceptual checkpoint questions are good. Especially 20.27 and 20.28. So these are some of the ones you should maybe take a look at, and we'll also take a look at some of these in the live or Zoom meeting office hours. Okay, so I'll sign off on this one and see you in the next section.